Hi there. This time I wanted to show you something really different, a small RF electronics building block that you can use in your circuits, and it's quite interesting. It's a very low cost circuit, and it's useful in many cases, especially on RF circuits. So let's dive directly into the circuit. This is the circuit that I wanted to show you. This is a transistor, BJT transistor amplifier, and this is quite straightforward. The bias resistors, and you notice equal resistors here. And what this is all about is this is a phase splitter, an accurate phase splitter. It can accept an RF signal at its input and split it into two phases, 0 degrees and 180 degrees. And it's not supposed to amplify the signal a lot. It's supposed to split the phase as accurately as possible. Now the same thing you can do it with a transformer. However, as you know, transformers are more difficult to build sometimes, especially from inexperienced hams. So the circuit doesn't have any inductor, and it's really straightforward. And it actually works pretty well. The key thing to achieving a good phase difference, a good 180 degrees phase difference between these ports is to use a high frequency transistor, the BFR 90A. You can use BFR 91 or other high frequency transistors. These are rated for an FT of several gigahertz. So that's the key point of achieving a good 180 degrees phase difference. For example, if you substitute this for a 2N2222, you will have something like I think 17 degrees of imbalance between these ports, right? So one port will not be 180 degrees offset from the other. It will also be an additional of 17 degrees plus or minus. So that's a key point, and according to some forums, this circuit is able to, for very good performance, it's actually able to do with less than 1.5 degree of phase imbalance at 30 megahertz. So that's a very good circuit for its cost. Okay, if in comparison, I have here, let me pull this out on the box. I have here this kind of splitter from Mini Circuits, which is the MCL PSC2-1. So these modules are of very good performance. These are of course passive. These are transformer based. So these are passive. They have a very good performance, but they are super expensive, right? For just a phase splitter, of course, they can tolerate about 1 watts of input power, I think. So very good circuit, and a very low cost circuit that you can build, and it works from very low frequencies down up to many hundred megahertz. I would say it depends of how strict you are in the phase imbalance that you want to achieve. So I wanted to test this circuit. I have actually tested this circuit before. I tested it in the oscilloscope. I have taken the trouble to use this circuit and just trust the LTSPI simulation. But now I'm gonna test this circuit, and as you can see, I have built it in open style and onto a piece of PCB board, and with a few connectors, and just this basically. powered by my lab power supply at 13.8 volts at 15 milliamps, okay? And I'm driving it with a generator at about 300 millivolts peak to peak at 50 ohms, okay? This is the port, the input port. And those two are the output ports which go to the oscilloscope, to the two channels. And I have set the oscilloscope to trigger on port number 1, so it actually triggers on the 0 degrees signal, and this is the top one that you see here, and in order to stabilize the waveform so you can also see the bottom one. So here we go. Now these two pieces of cables are actually of the same length, and actually they are of the same type. These are RG223 cables, but they are from different manufacturers, and they have also different connectors here. So usually we would expect exactly 180 degrees of phase difference between the emitter and the collector, but this is not the case, as you can see here on 30 megahertz. We have an offset, and I have set the markers here. We have an offset of 2.7 nanoseconds, okay, which is about, I think it's about 30 degrees of offset. That's too much. However, when I switch to a lower frequency, let's say all right, this is about give me a moment, let's read the dial. This is about 2.6 megahertz. When I switch to 2.6 megahertz, you will see that the phase imbalance is very, very little, okay? So the effect is more pronounced as we switch to higher frequencies. Now here I am at, just like before, at 30 megahertz, and that's the worst case scenario, and it shows 2.7 nanoseconds, okay? So I scratched my head and I said it can't be 30 degrees of phase difference. It must be something else. I mean, in theory, the circuit should be able to achieve 1.5 at least degrees of phase imbalance. So finally, I found what was the problem, and the problem is these cables. They are the same length, they are the same type, the same model, but these are from different manufacturers and the connectors are different. And I proved that by changing one cable, replacing one of the two cables with another one. And actually this is a much longer cable. It's about double the size. So I thought that on HF it wouldn't matter a lot, but it turns out that it does matter. And I'm doing it just now. I'm replacing this cable so you can see it. And remember, before the difference was 2.7 nanoseconds, and now, sorry about the camera shaking here, I'm trying to stabilize this camera tripod. So now if I put on the markers, marker number 2, now it's 1.7 nanoseconds, okay? So it's clearly the cable that is causing this, and I don't have any means, I don't have similar cables, I don't have exactly the same cables and connectors to test it. So I did another test to verify that the splitter works as intended, and let me switch back to the other cable, the previous cable, and I want to show you something. All right, And let's set again our markers here just to see the offset, the imbalance, I should say, phase imbalance. Okay, so I think this one needs a little bit, yeah, just about at right 2.7. So the thing here is that how one could test this to know that this phase splitter works fine. And the way I tested it is I built another circuit which uses just this mini circuits module, the PSC2-1, and I just put the PSC2-1 here instead of the active circuit, and those 3 coupling capacitors to the ports, and I actually measured the thing with exactly the same cables, coaxial cables, and guess what? I had exactly the same phase imbalance at 30 megahertz, 2.7 nanoseconds. And as I switched back to the lower frequencies, I was seeing a better phase imbalance, okay, less phase imbalance at lower frequencies, just like with these active circuits. So from that, I know that this circuit works at least very similarly to the original, the mini circuits phase splitter. And the mini circuits phase splitter, if you give me just a moment, as I'm looking it now, just a moment, I want to find out the phase. Yes. All right, just a moment. Yes. And according to the mini circuits, at 40 megahertz, which is 10 megahertz above this frequency, at 40 megahertz, the mini circuits module should have a phase imbalance of 0.02 degrees. Okay, that's excellent phase imbalance. So I cannot measure such a low phase difference, of course, with this setup here, but by setting up the markers really at the same position, at the very bottom of this waveform and at the very top of this one, I can measure again 2.7 nanoseconds with the mini circuits, and also 2.7 nanoseconds at 30 megahertz with this phase splitter. So from that I know that this phase splitter is very close to the mini circuits one. Okay, in theory they say that in the forums that is 1.5 degrees at 30 megahertz, but I cannot verify such a low phase imbalance. So it works really well, and we have proven this with this indirect, say, way that it works really well. So I hope you enjoyed this video. This is a very helpful circuit for your RF experiments, and not only, I guess you can use this circuit also for audio if you make those capacitors large enough. I guess you can use this circuit for audio. Okay, this is a multi-gigahertz transistor, so you can use it instead of a transformer phase splitter, 100 degrees phase splitter to drive push-pull amplifiers. The same for RF. So I hope you enjoyed this video, and thanks very much for watching. Here is Sierra Victor 3 Oscar Romeo Alpha. Thanks a lot.